two ice sheets in the world, Antarctica and Greenland. They differ in that Greenland is mostly about its interaction with the atmosphere. So when the world gets warmer, Greenland melts more because the air temperature is greater. Antarctica, because it's at the South Pole, is very much colder, and the way climate affects Antarctica is through changes in ocean water temperatures. So they're very different things, although they're both similar sort of sizes, hundreds of thousands of kilometers wide, kilometers deep. A tipping point for Greenland, it works in the vertical, if you like. So we know that as you go up in the atmosphere, things get colder, and that means there's less melt and more snowfall. So, and we also know that as Greenland melts, its surface gets lower. So in the future, Greenland's likely to melt, and therefore its surface is lower in the atmosphere. It will experience warmer temperatures and more mass loss. So you can see there's a positive feedback there that as we start to melt Greenland, its surface lowers, it warms, and we get progressively more and more mass loss. So that's called a positive feedback, and that leads to a tipping point. And this one's called the surface mass balance height feedback. It's been known in Greenland for at least 30 or 40 years that this exists in theory. A lot of research has gone on to exactly what that means for Greenland. Is there a threshold in terms of global warming that triggers this irreversible retreat of the ice sheet? For Antarctica, it's different. It's not a vertical change, it's a horizontal one. So as ocean temperatures increase around Antarctica, Antarctica shrinks in terms of the area it occupies. And as it shrinks, the thickness of ice exposed to the ocean becomes larger. That means more mass is lost from the ice sheet, and you get the same sort of feedback occurring, triggered by an ocean warming. And the ice sheet initially gradually retreats, and then as it retreats into deeper and deeper ice that loses more and more mass, it potentially continues to retreat until it just disappears. So that's the other type of tipping point that we're dealing with. Much of what we know about tipping points has been developed on the basis of very simple models of the system. These are used because they're easy to analyze, and you can generate assessments of their stability in a very generic way. However, we know that those models are a gross simplification of reality. So what we're doing now is gradually moving from the very simplest models that we know tip to reality that we're not certain whether it tips. And as we gradually increase more and more physics, more and more coupling to the rest of the climate system, it's interesting to see whether that changes the fundamental tipping character of these things, which we know exist in principle, but we're yet to establish whether it exists in practice.